Hi everyone. Today we're going to be talking about Endianness, specifically what it means to be little endian versus big endian, and why that's important for computing. Let's get started. The word Endianness actually comes from the story of Gulliver's Travels by Jonathan Swift. In the story, Gulliver finds himself on the island of Lilliput, whose inhabitants often quarrel over trivial things. As the story unfolds, the Lilliputians become divided over the matter of whether to crack a soft-boiled egg at the little end or the big end. Those that crack the egg at the little end become known as little endians, and those that crack the egg at the big end, big endians. And in the story, a war is waged between the two rival parties. In computing, we have a similar decision to make. Given a multi-byte piece of data, like a number, how should we represent it in memory? Should we put the most significant byte first, which would be big endian, or should we put the least significant byte first, which would be little endian? To clarify what I mean by most significant, consider the decimal number 512. The 5 is the most significant digit because it actually represents 500. Similarly, in this hex number, the first byte is the most significant because it actually represents this number. And you can think of the most significant byte as the one that carries the most weight. Let's explore endianness a little more. Assuming that we read left to right like in English, humans write numbers in big endian. We actually know this from the previous example where we wrote both 512 and this hex number with the most significant digit or byte first. These numbers are both in big endian from left to right. It's also helpful to separate the value of a number from its representation. These are all different representations of the same value 16. Just like both of these memory representations are valid representations of this number, but one is little endian and one is big endian. Looking at things this way, we can see why it's important to agree on endianness. If we don't know the endianness of a representation, we don't know what value is being represented. Is this number hex AABB in big endian, or is it hex BBAA in little endian? There's no way to know from these numbers alone. That's why when machines communicate to each other, over the internet for example, they must agree on endianness. According to the internet standards in RFC 793, all the fields in network headers must be big endian. So if a computer speaks little endian, it must convert the values in the fields to little endian before interpreting them. To finish up, let's talk about a few places where people often stumble with endianness. First, endianness is about byte ordering and not bit ordering. The bits are not reordered. If you find yourself talking about bits and endianness, it probably means you're on the wrong track. Secondly, endianness only applies to multi-byte values, meaning that if we only have one byte, there's no such thing as endianness. This has some implications that might not be obvious. For example, let's say we have an ASCII encoded string, John, with each character being its own byte. In this case, talking about endianness wouldn't really be meaningful because each byte is its own value. John wouldn't be represented like this because the values we're talking about here are characters, which are each one byte, so there's no endianness. Lastly, I want to talk about debuggers and endianness. Since the hardware takes care of endianness for us in most cases, you shouldn't have to worry about it much if you're a programmer. That being said, it can be extremely confusing to inspect memory using a debugger because you might see some unexpected values. Let's take this hex number for example and assume that we're using hardware that's little endian. That means that when we store this number, the processor will store it with the least significant byte first. When we're debugging, this number will probably be in memory somewhere, and with the debugger you can usually inspect memory manually. If we ask the hardware to read a 4-byte number starting at this address, we get back the expected value because the hardware will do the endian swap transparently for us. The confusion comes if we ask the hardware to read 1 byte at a time, which would give us this, or if we ask the hardware to read a pair of 2-byte values, which would give us this. Remember that the hardware will do the endian swap for us, so if we don't read the value with the correct size read, we may see the bytes in an unexpected order because the hardware is trying to do the endian swap. That's all for this video. Hopefully you learned something cool about endianness. See you next time.